Hello everyone, in this video I'll be talking about our MM' 2022 paper, Model Guided Multi-Contrast Deep Unfolding Network for MRI Super Resolution Reconstruction. Our work is available as open source GitHub. Magnetic resonance image with high resolution provides more detailed information for accurate diagnosis and quantitative image analysis. However, in real-world cases, MR images are often obtained with a longer scanning time, lower signal-to-noise ratio, and small spatial converge. Additionally, the quality of MR images acquired in clinical practice may be insufficient owing to patients' involuntary physiological movements during the acquisition process. This is particularly problematic when protocols requiring a long echo time or repetition time are used. These scans may lead to inaccurate diagnosis as limited structural and textural information provided in subsequent quantitative medical image analysis. As a result, there is emerging interest in developing super-resolution techniques for reconstructing high-resolution outputs from low-resolution images to increase the spatial resolution. The utility of super-resolution is capable to improve the quality of MR images without modifying the hardware and overcome the challenges in obtaining MRI scans. Existing techniques for image super-resolution reconstruction include model-based and learning-based approaches. Model-based techniques utilize domain knowledge when modeling the physical mechanism underlying the issue. Alternatively, deep learning-based SR approaches have gained growing attention in recent years. Nevertheless, all of them are designed in a black box principle, thus lacking sufficient interpretability and further limiting their practical applications. Interpretable neural network models are of significant interest since they enhance the trustworthiness required in clinical practice when dealing with medical images. Besides, most existing SR reconstruction approaches only use a single contrast or use a simple multi-contrast fusion mechanism, neglecting the complex relationships between different contrasts that are critical for SR improvement. To deal with these issues, in this paper, a novel model-guided interpretable deep unfolding network for medical image SR reconstruction is proposed. Model-guided image SR reconstruction approach solves manually designed objective functions to reconstruct MRI. We show how to unfold an iterative MGDUN algorithm into a novel model-guided deep unfolding network by taking the MRI observation matrix and explicit multi-contrast relationship matrix into account. An outline of the overall process is shown in this figure. Next, we briefly describe our method and experiments. It is assumed that an LR image is obtained by downsampling and blurring an HR image. So the linear relationship between the observed image and the original HR image can be typically formulated as follows. Transform modal relationship considering multi-contrast MR images in MCSR task. The transform relationship between the guide image and the unknown original image can be formulated as follows. As a result, Z can be obtained by solving the following objective function, where the last two regularization terms correspond to the prior domain knowledge of the MCSR task, which are noise prior in the typical degradation process and transform modal noise prior in multi-contrast image, respectively. The choice of various regularization functions reflects different ways of incorporating prior knowledge about the unknown original MR image. Following the framework of half-quadratic splitting to introduce two auxiliary splitting parameters U and V for Z with the different prior knowledge of the MCSR task. The equation can be formulated as a non-constrained optimization problem, which can be written as To obtain an unrolling inference, equation can be divided into the following three subproblems and solved alternatively. For the objective function of equation with the prior knowledge of the MCSR task, we employ the efficient proximal gradient descent to solve the above three subproblems. Inspired by the principle of model-driven deep learning, we generalize these equations as a network block. Each step is translated with deep learning terminologies. In each network, two auxiliary variables are updated first. Due to the existence of noise, the prox operator can be implemented by a deep denoising module. Then, we reconstruct our estimated HR image. In our network, the reconstruction process, which is implemented by a reconstruction module, consists of cross-modal transform module, downsampling block, and upsampling block. Therefore, the reconstruction process in the neural network is as follows. Where up and down denote the upsampling and downsampling operator in spatial resolution, respectively, and P and PT perform the cross-modal transform functions. Then, the updated Z is fed into the next stage to refine the estimate U and V again. The denoising module and the reconstruction module are alternatively updated T times until reaching the final reconstruction. Our MGDUN is supervised by the L1 loss between ZT and the ground truth Z. About the deep denoising module. In this paper, we have adopted a variant of UNet as the backbone of deep denoising module. Other more effective networks for medical image denoising can be also adopted. In cross-modal transform module, we find that P and PT perform a cross-modal transform operation, and the two processes are inverted. One from the target contrast image to the guide contrast image, and the other from the guide contrast image to the target contrast image. As a result, we design cross-modal transform modules using the principle of invertible neural networks. The pair of operation DKT and DK can be implemented by upsampling and downsampling layers for modeling capability. The operators DKT and DK are simulated using a convolution network layer respectively. Our experiments are implemented on the IXI dataset as well as on the BRATS dataset. The IXI dataset contains registered T2 weighted and PD weighted MR images of 578 patients. T2 weighted images were used for SR and the PD weighted images served as the guidance. The BRATS dataset contains multimodal brain data, including registered T1, T1C, T2, and PD weighted images. Similar to IXI dataset, we chose T2 weighted images for SR and T1 weighted images for guidance. We compare our results with a number of models including classical methods, single contrast methods, multi-contrast methods, and unfolding methods. More specifically, the proposed method is compared with bicubic, EDSR, MDSR, RCN, COISTA, T2Net, and ISANET. For quantitative evaluation, we utilize the average PSNR, SSAM, and MSA. This table reports the target contrast reconstruction performance on different datasets under 2 times and 4 times enlargements where the best and second best values are highlighted. It is clearly noted that our method achieves the best performance on different enlargements of different datasets. The results demonstrate that our model can effectively fuse the two contrasts, which is beneficial to the SR reconstruction of the target contrast. This substantiates the effectiveness and flexibility of our method with a certain degree of generalization. We provide qualitative comparison results on the IXI dataset as well as on the BRATS dataset and their corresponding error maps. The texture of error maps represents the restoration error. The smoother the texture, the better the reconstruction. As we can see, the input has significant aliasing artifacts and lacks anatomical details. It can be noted that our model recovers the image with fewer visible artifacts and reconstructs more details than other competing methods. To further verify the performance of the proposed model under different configurations, a series of ablation studies are carried out, including effects of the number of stages. Influence of the guide images, effect of the number of INN blocks in cross-modal transform module, effect of the denoising modules. To demonstrate the trade-off between the cost and the performance, we compared this against several existing SCSR methods in this table. It's noted that our model can achieve better performance than others with comparable model sizes. Although it does not achieve the best performance in terms of testing time, the proposed method still has notable advantages over other competing methods. The results demonstrate that our method can yield satisfying performance with a good trade-off between cost and performance compared to other deep learning-based methods. In conclusion, we design a novel model-guided deep unfolding network for medical image SR reconstruction, which models multi-contrast MRI SR with other contrast images in an interpretable manner. We elaborate on how to solve the manually designed objective functions and how to unfold the iterative algorithm into a neural network by incorporating domain knowledge. We reconstruct an HR image of a target contrast from an LR input with the aid of other guide contrasts, providing a new strategy for multi-contrast fusion. Extensive experiments on multi-contrast IXI dataset and Brat's 2019 dataset demonstrate the superiority of MGDUN. Thank you for your listening.